So now we come to the math section of acids and bases, and it's all to do with pH and autoionization of water. So pH, something you've probably heard before, you probably don't understand it. Autoionization of water, probably don't know what that means either. That's okay. Hopefully after today's video, you'll have a better understanding of pH and autoionization of water. Let's start with autoionization. So water can dissolve salt. If I put solid sodium chloride crystals into water, I will get sodium ions and chloride ion. Because water dissolves salt, because salt, sodium chloride is ionic, water is polar, they're both charged, and they dissolve each other. The water just dissolves salt. Water dissolves a lot of things. It's called a universal solvent. That's bogus. It's not universal. It's just very common. It can dissolve a lot of things, right? It can dissolve a lot of things. It can dissolve pretty much anything with a charge. But water has a charge. So can water dissolve water? If I put water and I mix it with water, and stay with me here, I'm not talking crazy, can it dissolve itself? And the answer is yes. Water can dissolve itself. If you put water and water together, one molecule will gain the hydrogen and one molecule will lose the hydrogen. That's why this is called autoionization. It's ionizing itself. It's just ionizing itself. And let's do some review here. Let's make this my Bronsted acid, and let's make this my Bronsted base. And let's label some conjugates, because we love doing that. So if this is the Bronsted acid, then, and if this is the Bronsted base, if this is the base, this is the H2O, if this is the base, it is going to lose an H+, it's going to gain, base except, it's going to gain an H+, and it's going to turn into this, which is the conjugate acid, which would make this, of course, the conjugate base. There we go. Just like that. Alright, so water can dissolve itself. So the question is, how much does it dissolve itself? Like if I had a glass of water, how much of that water would be hydronium hydroxide? Like these are two very dangerous molecules. Am I going to die when I drink water? No, of course not. You're not going to die. You drink water all the time. It's because it's a very small amount. It's very, very little of this actually dissolves. Very, very little. Matter of fact, if I am at room temperature and I have 1 liter of water, it's not a ton. How much of that is going to be hydronium, and how much of that's going to be hydroxide? They're going to be this equal amounts because of, if they make one, you make one of these, you make one of those. So I have 1 liter of water. I have about 1 times 10 to the negative 7 moles of H+. Alright, that is 0.00000001 moles. That is not a lot. 1 liter of water will also get me about 1 times 10 to the negative 7 moles of OH-. So, water self-ionizes, but not very much. Like it's very, very small amount, which is why it's not dangerous to drink water. Alright? We discovered this because there was a Swedish scientist, I think it was Arrhenius. Is the one that, or no, it was a Danish guy. I don't remember. There was some old dude who started messing with the conductivity of water. So we thought water was this. That has charges, but the electron's not really free to move, which means this should not conduct electricity. But it does. Water does conduct electricity a little bit. So he theorized that water must be dissolving itself and making these charged particles, so it couldn't conduct it, and he was right. That's exactly what it's doing. So here we have very small amount of H+, very small amount of OH-. So what does this have to do with the pH scale? All right, some of you probably already see this. pH stands for, so pH, lowercase p, uppercase h, I think it's better and should be seen as lowercase p, uppercase h plus. I like that better because that's more accurate. Because what this pH stands for is the power of hydrogen. That's what it stands for. And it is a lowercase n, p. I think it's originally in like German or something, and it was like the word was like potens or something. It doesn't matter. It still means power. It's the power of hydrogen, or H plus is a better way to look at it. Power of the hydrogen ion. What does it mean by power? Literally power, as in like the power. This is 1 times 10 to the negative 7. This is the power. So the power of hydrogen, the pH of water, do you guys remember what the pH of water is? The pH of water is 7. Uh-oh. Yep. There it is. That's 7. That's where that 7 comes from. The reason 7, which is neutral, the reason water is neutral is because the amount of H plus you get at room temperature in 1 liter is 1 times 10 to the negative 7. So what happened to the negative? Well, we just ignore the negative. So what you end up doing is you take the power, which is to the 7th power, you change the sign, and it becomes a pH of 7. So that's what neutral is. The equation then, if you want to know the equation behind this is the negative log of the hydrogen ion concentration is the pH. Just like that. Alright? So the negative log of the hydrogen ion concentration is the pH. So you guys probably know that the pH scale ranges from like 0 to 14, with 14 being basic and a 0 being acidic. And water is 7, which is neutral. You probably know that. The reason it's 0 to 14 is, 1, it's not 0 to 14. You can actually have something more basic or more acidic. You can have a negative pH if you want. There's negative 1, right? You can have that. There's nothing wrong with that. You can even have a pH that's 15. There's nothing wrong with that, all right? These numbers, think of it this way. The pH scale is for stupid people. Because if we told people that their water had 1 times 10 to the negative 7 moles of H plus in it, they would have no idea what you're talking about. They have no idea. They would have no clue. So they say, okay, we'll ignore the 1 times 10 part and ignore the negative and just say 7. The pH of your water is 7. And they're like, okay, I can understand 7. That pH of 7 means that. There's that much, which is not much, which is why neutral water is quite safe. Okay? The moment you start to get away from that is when you start to get the dangerous stuff, right? So if the pH goes one way or the other, doesn't matter which way it goes, you are going to get a much more dangerous situation. Because remember, at pH of 7, which is 1 liter of water at room temp, let me make sure I put that at room temp because it will change the temperature, but don't worry about that. At room temp, then it's 1 times 10 to the negative 7 moles of H plus and 1 times 10 to the negative 7 moles of OH minus. So, does that mean there is a POH scale? Right? Can we look at just the power of hydroxide? And the answer is yes. Yes, we can. There is a POH scale. So POH is just the opposite of pH. Okay? This is the power of hydroxide. Okay? It also is roughly negative 1 to, 15 or so. 7 is still neutral. But, negative 1, 0 down here. This is actually the basic end. And this is the acidic end. We do not use the POH scale very much. You do need to be able to flip back and forth between pH and POH. It's very easy. pH plus POH will always equal 14 at room temperature. Alright, so pH plus POH will equal 14. So if the pH is 7, the POH is 7. If the pH is 8, the POH is 6. Alright? 7 plus 7 will equal 14. 8 plus 6 will equal 14. 6 plus 8, so on and so forth. It has to equal 14. Okay? And to find pOH, it's very similar. You take the negative log of the hydroxide concentration. So let's talk about log for a second. I'm not going to get into all the details of logarithms because they suck. However, I will tell you that for us, we all deal with log base 10, which means it's 1 times 10 to something. So 1 times 10 to the negative 1. The negative log of that would be 1, right? Because you take the log of that number and then change the sign. You're going to need a calculator for this section, so make sure you have yours out and handy, and make sure you know how to use the logarithm. Mr. Lockyer posted in his notes a very good step-by-step what buttons to hit on your calculator. The problem is not every calculator is the same, but it's still a good place to start how to solve these problems. Okay? It's about taking the negative log of the hydroxide concentration. Now, he goes one step further and says that, okay, given the pOH, right? So if I told you that the let's do pH, because pH is much more logical. What if I want to know the pH and the hydrogen ion concentration is 1 times 10 to the negative 8? Let's just say. No, that's not it. Let's do 1.5 times 10 to the negative 8. All right, and I want to know what the pH is. So pH equals negative log of the hydrogen ion concentration. Okay? This is the hydrogen ion concentration. So you just plug this number in. pH equals the negative log of 1.5 times 10 to the negative 8. So how do you do that? Ignore the negative. You'll do the negative at the very end. What I usually do is on the calculator, depending on how your calculator works, you either hit log and then the button, or the button and log. So mine is, I actually have to hit log first. So I hit log, and I want the, and honestly, you could probably do this all in one step on a calculator like this. I could hit negative log, and then actually do it if you wanted to, if you have a fancy calculator, but if you don't, you might have to hit in the number first, then hit log, or you put the log first, then put the number. Your calculator is different. Look it up. Teach yourself how to use your calculator, or you can ask me. You can ask me, and I can help you as best I can. Send me pictures. I'll see what I can do. Take the log of 1.5, and then how do I put in times 10 to the negative 8? Oh, it's been a while. It's been a while, but it's easy. It's EE. All right. Times 10 to the... Uh-oh. I don't hit the right button. This is my wife's calculator. Look at me. Like, you need to know how to use your calculator. I don't know if I can. Let's see here. I don't like this. 1.5. Where's my EE button? That's not it. That's the anti-log. Where's the EE button? You guys are looking like it's right there, Mr. Harmon. Like, oh, there it is, right there. All right, 1.5 times 10 to the negative 8, like that. Then I hit enter. Okay, that did not work. There, I can't have a parentheses there apparently. So I got negative 7.823. So the pH equals negative 7.8239, so on and so forth. Okay? These negatives will then cancel, so my pH is 7.8239. Sig figs. Ooh, sig figs are complicated. Alright? If you thought that's 2 sig figs, and you put your answer down like this, that is wrong. That is not 2 sig figs. I hate to say it. pH is weird. That's actually 1 sig fig. Don't ask. Don't worry about it until, AP or Chem 2. You will not be asked to do something like that. Just put in it. Keep all your digits on Quest and you'll be fine. That's actually 2 sig figs, 7.82. Only the decimals count. This first part doesn't count. This is the only part that counts. This only happens for pH. It's logs. I told you, man, logs suck. Don't worry about it, though. All right? So, what if it's the other way, though? What if I have, instead, I give you the pH. I say the pH, I tested my pool, and my pH is a 2.43. First off, don't get in that pool. You will die. I'm just kidding. You won't die. It'll probably just leave a horrible rash. Don't get in that pool. I want to know what the hydrogen ion concentration is. Okay, that's what I want to know. So how do I do this? Well, use your equation. pH equals the negative log of the hydrogen ion concentration. Problem is, what do you do with a log? How do you get rid of a log? Okay, so a log base 10. Do I divide by log? No. First thing I'll do is get rid of the negative sign. So I'm going to flip it over here and put negative 2.43 equals the log of the hydrogen ion concentration. So some of you are good at math and you know exactly how to do this algebra. Others are like, I don't know what to do. Okay, so here's what you do. To get rid of a log, you take 10 to that power. So you take 10 to this. If you take 10 to this, the log cancels. So of course, if you do it to one side, you do the other side. So you take 10 to that power right there, right? So 10 to log cancels. And so H plus equals 10 to the negative 2.43 power. So H plus equals 10 to the negative 2.43 power. So how does one do that? Well, if you look on your most calculators, on the opposite of the log is the anti-log button, which is this right here. So 10 to, what did we say it was? Negative 2.43. And we'll get our answer, 0.003715. And it is molarity, which is moles per liter, and that is my hydrogen ion concentration. That's it. That's it. What if I had asked for a hydroxide concentration? Well, for hydroxide, you need POH. And to get POH, you have to remember that pH plus POH will always equal 14 at room temperature. So convert to pH first, then go from there. But the math is exactly the same. There are only two different ways we can ask this question here. We'll either give you the pH and ask for H plus, or I give you good God, or sorry about that, just whack the camera, or I will give you the concentration and ask for the pH. That's the only two ways to ask this. And that's all your math problems are, it's just that over and over again. So let's take a look at some problems, because of course it's going to get a little more complicated than that. We're always going to throw some weird curveballs at you, because it's chemistry. Let's see here. All right. Whoop, just ripped the worksheet. That's fine. Let's do some of these. Here's your worksheet here. There's lots of practice problems. I'm going to do as many as I can with you. And then I'll let you go and let you work some on your own. All right. Calculate the pH of the following solutions. 0.00534 molar nitric acid. All right, so nitric acid is HNO3. If you don't know that, look it up. Okay, it's HNO3. How many H's does that have? It has one. Nitric acid is a strong acid, which means for every HNO3, we get H+. So 0.00534 molar HNO3 will give me 0.00534 molar H+. Okay? I'm actually going to go back to the paper. I like the paper better. I think it shows up better and I'll have more room. So I'm going to go back to the paper. I'll just keep swapping back and forth here. 0.00534. So the question is, what is the pH? pH equals negative log of 0.00534. So how do you do that in a calculator? Every calculator is different. Mine's going to be this way. I'm going to put in, actually I'm going to put all of it in at once, negative log of 0.00534. And I get a pH of 2.272. Again, don't worry about sig figs. pH of 2.272. That's it. No units. No units. Sig figs. That's the correct number of sig figs because this is 3, and that's technically 3. Don't worry about sig figs though. Just keep as many as you can in Quest. 2.272. That's it. That's all. That's A. That's 1A. Done. All right. 1B. I'm going to do all of 1 because there's some weird things. Sodium hydroxide, I got 0.0000. Oh my god, how many zeros is this? 1, 2, 3, 4, 5. 0, 8, 9, and again, 0. molar NaOH. Alright. So, first question you ask yourself is, how do you go from molar of the base, or the molar of the acid, to the molar of the hydrogen, or the molar hydroxide? Well, you look at it. How many hydroxides does this have? Just one. So, that many, which by the way, let's turn this into 1, 2, 3, 4, 5, 6. 8.90 times 10 to the negative 6 molar. We're not barbarians here, we can use scientific notation. Of NaOH is the same as 8.90 times 10 to the negative 6 molar OH. They are the same because it's 1 for 1. For every one of these, you get one of those. I keep mentioning this because the next two aren't going to be that way, and you'll see it. Alright, so I want to know the pH. The problem is I have the hydroxide concentration. No problem. If I can calculate the pOH, getting the pH is super easy because pH plus pOH equals 14. So let's find the pOH. pOH equals negative log of the hydroxide concentration. Okay? So all I have to do is take the negative log of 8.96 times 10 to the negative 6 molar of the hydroxide. So I'm going to put in my calculator. Oh, forgot the negative. There you go. Negative log 8.96. Lily is trying to break in. 8.96 times 10 to the negative 6. And I got, for my pOH, 5.04769. Okay? So what's my pH going to be then? Well, if I want to know the pH, pH is simply pH plus pOH has to equal 14. So simply subtract 14, subtract that number right there, and we got it. .952 is my pH. There we go. That's B. 1A, 1B. The trick in this one was it gave me OH and I wanted pH. If I want to, if I do that, just subtract 14 once you get the pH and pOH. Not that bad. 1C. Alright. 0.00. Oh my gosh, what's with these people? 0.00000 143 molar oxalic acid. Oh, I don't know what oxalic acid is. What are you, Mr. Harmon? Look it up. Look it up. It's H. C2O4. That's oxalic acid. Oh, H2, C2O4. That's oxalic acid. So, what's tricky about this one is that there are two H's. Okay? There are two H's, which means that for every one of these, we get two H's, which means we got to take our concentration of that times 2. Once again, because there are two H's in H2CO2O4. If I put that in water, two H's are going to fall off. Alright, so for every one of these, I get two hydrogens. For every one of these molecules, I get two hydrogens. So I have to take this times 2. So 143 times 2 is, oh my god, put this in scientific notation. You people and these long numbers. I do not know how to put this calculator in scientific notation. It stays the way it is. 0.0000286, which is the concentration molarity of H+. So now, if we will find the pH, it's easy. pH is just negative log 0.0000286. So I'm going to take the negative log of the number I had up here. This calculator is fancy, I can just grab it. And I get pH of 5.54. How many tick figures am I going to keep here? It doesn't matter. because, like I said, sig figs are weird with pHs. 5.5436. Let's just say that. I should keep 3, so I should get rid of that 6. But it doesn't matter. 5.536. 5.5436 is the pH of this solution. Oh my gosh, you guys can't see my answer. There it is. 5.536. 5.5436. Alright. Part D. 1D. 0.00870 molar magnesium hydroxide. Where did you get the OH2? Magnesium's +2. OH is -1, so I need 2 OHs. Which means that for every one of these, I get 2 OHs. Which means I gotta take this concentration times 2. Keep an eye out for that. Keep an eye out for that. If you forget to do that, the whole thing's wrong. So that is my concentration of OH minus. So now all I got to do is take the negative log of that value, and I will have myself the POH. So POH equals negative log 0.0174. Negative log of 0.0174. And I get the POH 1.7595, something like that. And you're done. And you're wrong. Because you're not done. What the question asked for. Wanted pH. Ah, dang. I want pH. I have POH. No problem. Just take 14 minus this number right here. And you'll get your answer. So 14 minus what I just got. And I get for my pH 12.240 is the pH. Keep an eye out. What are they giving you? What are you trying to find? So, I just did 1 through D. Or 1, A through D. I'm going to do number 2 now because I want to go back the other way now and show you how to do that. Alright? Then the rest of those, keep an eye out for molecules that have more than one OH or more than one H. Keep an eye out for those. You should be able to do the rest of this until we get to neutralizations, which I will cover in a separate video. So let's go back to 2 now. 2. 2 says, calculate the hydrogen ion concentration of a solution that has a pH of 5.45. 5.45. So, we know that 5.45 will equal the negative log of the hydrogen ion concentration. How do you get rid of a log? First thing I do is get rid of that negative. So let's flip the negative over here to negative 5.45 equals the log of the hydrogen ion concentration. How do you get rid of a log? You take 10 to the base, or you take its base to the power. So this is log base 10. They're always log base 10. So I'm going to take 10 to that side and 10 to that side. That cancels. So all I need is 10 to that, and I will have my hydrogen ion concentration. So 10 to negative 5.45, and I get, I really wish, wait, yes, I figured out scientific notation. Oh, happy days. Get 3.548 times 10 to the negative 6. Again, don't worry about sig figs. I honestly only have 2 there, 3.5, but not worry about it. Just keep as many as you can in Quest. And this is molarity because we're talking about concentrations here. Okay? Letter B. Letter B. POH equals the negative log of the hydroxide concentration. I want the hydrogen ion concentration. That's okay, because if I solve for the Oh, you're right. Why would I do that? 2b is asking for the hydrogen ion concentration, right? I need pH. So the first thing I should do is turn my POH, so we don't need that at all, is turn my pH, which is 11.34, into the pH. And to do that, you just take 14 minus 11.34, and you will get the pH. So 14 minus 11.34, and I get 2.66. Now that I have the pH, I can go back in and take 2.66 equals the negative log of the hydrogen ion concentration. Switch the negative to the side over here, so negative 2.66 equals the log of the hydrogen ion concentration. Take 10 to that power, like that, and I get a hydrogen ion concentration that equals 10 to the negative 2.66. And I get 2.188-ish, somewhere in there, times 10 to the negative 3. Molarity, moles per liter concentration. Okay? So that is how you do questions like that. And the next two are exactly like the ones I just did here. Alright? So give those a shot. You should be able to do all of 3, all of 4. And can't do 5, 6, 7, or 8 yet. So just do 3 and 4 on this. And then the other worksheet. Where's the other worksheet at? The other worksheet, this guy right here. You should be able to do all of these. You should be able to do all 39, 40, 43, 44, 45, 46. You should be able to do all of those, no problem, because there is no anything talking about neutralization. Yep, should be able to do all of that. The answers, of course, will be posted as well. The only thing you can't do is 5, 6, 7, and 8 down here, because that has to do with neutralizations, and I will show you that in the next video. Alright, see you guys.